Now let us look at the boost converter waveforms. This is the boost converter. I hope you recognize this topology. The inductor is on the input side, and when this BJT is on, you will see the inductor current flowing in this direction, charging up the inductor. When this is off, you will see the inductor current pumping current into the output capacitor and the output load. So the base drive or the gate drive for this power semiconductor switch, which is given here to turn it on and off, is shown here in the G, like before as in the boost buck converter. So when this signal is high, the transistor is on. When it is low, the transistor is off. So that is what we use as the convention here. And during the time when the transistor is on, BJT is on, it is the period DTS, and during the time when the transistor is off, it is called period 1 minus DTS. Now take the pole voltage. Here also the two critical things is the pole voltage we have to see, and the current through the inductor. These two will give the information to rate your devices and components. So as before, the pole voltage here is easy to deduct. So when the device is on, the pole voltage here will be 0. So whenever the gate drive is given, the pole voltage will be 0. And whenever this is off, the diode is conducting, the inductor will charge to the send the charge to the output. So when the diode is conducting, the output is connected to the pole, so it will be V0 point. So it will be 0, goes to V0, then goes to 0, and goes to V0, so on and so forth. So let us put that waveform here. So this is the waveform that you would expect to see in an ideal case at Vp, the pole voltage. And we know that this is V0 value because when the transistor is off, diode is conducting, and the V0 point and the Vp point are same. So which means that in the case of boost converter, the V0 is actually the maximum value of the pole voltage. So looking at this pole voltage, you can rate the transistor and the diode. So during the time DTS, transistor is conducting, diode is off. So what should be the diode withstanding capability? This point is connected to 0, this is 0, and this is V0. So the entire V0 value is coming as reverse voltage across the diode, and the peak inverse voltage for the diode should be V0. That is one rating which you can have for the diode. Yeah, and likewise for the BJT, when the BJT is off, diode is conducting, V0 value comes in here, and the BJT should withstand V0 during its off condition as seen from this waveform. So the voltage ratings for the two devices can be got from the pole voltage value. Now for the inductor current, so the inductor current will also go in with a triangular ripple kind of a wave shape as we discussed in the buck converter too, but only the values, the amplitude, the significance will be different. So let us say that we have an inductor current waveform something like this. It is rising with one slope and then falling with one slope and so on. Now the rising slope is during the time when transistor is on, which is Vp is connected to 0. So the rising slope is V in, the voltage across the inductor, by L. So this would be V in by L slope. And this falling slope is when this is off and the diode is conducting, and this point is at V0, Vp point is at V0. So the falling slope is V in minus V0. This is V in minus V0 divided by L. That would be the falling slope. Why do we say it is falling? Because the output voltage is greater than the input voltage, so V in minus V naught is negative, and therefore you have the negative slope. So this keeps continuing. The average value of the inductor current is not I naught as it was in the case of the buck converter. In the case of the buck converter, the inductor was on the output side, and therefore the average value directly indicated I naught. Here the average value is indicating the source current or the input current IN. Here also we can define delta IL, the peak to peak ripple amplitude of the current. Next, let us see the components of the inductor current. So during the time when the transistor BJT is on, the inductor current flows through like this. You have the inductor current charging up the inductor, and therefore it has to linearly increase. So let us put that current wave shape. So this is the component of the inductor current which is flowing through the inductor and the switch BJTQ. So this is IQ. And during the time when the switch is off, you will see that the current IQ is 0, and during the time when it is on, it just follows the inductor current. And during the time when the switch is off, the current through the diode should be the blank portion. The other portion, let me fill that in. So it would be like this. So the yellow regions are the parts of the current that flows through the diode. So that is also the current that is flowing through the capacitor or not combination. Let me remove out the blue region so that we have some clarity in the current flowing through the diode, and which will again split up into C and R naught, I naught current. Now this yellow shape, wave shape, is the one which is flowing through here, and this is having two components. One is the average component and the AC component. The average component will flow through R naught, and that is I naught, and the AC component, which is having zero average, should flow through the capacitance. Now let us say the average value of this current is placed somewhere here, and that would be I naught. The average component placed here, that would be I naught. So you will see the capacitor, this triangular portion up charging the capacitor, and this bottom white portion here I am indicating is the capacitor discharging into the load, this area should be same as this area. This triangular upper area and this area should be same to have charge balance. We will look at that shortly. So this is how the current wave shapes come into picture. And about the rating, if you take the current rating for the BJT, you will see that the average of the inductor current will be IN, and IN and I naught are related. If you use the amp second balance, you will see that IN into D is I naught, or IN will be I naught by D, and therefore you will know the average value for the BJT here. So the BJT has to be rated for this peak current here, which is IN plus delta I by 2. Likewise the diode, and the output average current I naught is a spec given to you, and it is actually the average value of the yellow portion of the waveform. Now let us look a bit closely at the current waveform so that we can calculate the values of C and L. In the case of the boost converter, we saw the inductor current waveform is something like this. So I will draw the inductor current waveform here, and we have seen that there is a kind of a triangle ripple like this. Now what we are interested is this average value, which we call I in, and the I naught value is somewhere here, and that is actually coming as the average of this currents, this part of the currents. We saw that just now, isn't it? These parts of the currents. Now, how are I naught and I in related? If V naught I naught is the output power and V in I in are the input power, we say that there is, in the ideal sense, there is no loss within the converter, because they are either using switched components or we have other components which are L and C's. Both are non-dissipative. So the input power should be equal to the output power. So these two should be equal. Now we know the relationship between V naught and V in. In the case of the boost converter, this is valid for any converter. V naught I naught is equal to V in I in. Now in the case of the boost converter, we say that V naught is V in by 1 minus D into I naught is equal to V in I in. So we can remove this, and then you say that I in is equal to I naught by 1 minus D. We get the current relationship. We can do it this way, or you can use the amp second balance in the capacitor to get the same relationship. So I in is can be found out because I naught is a spec, D is obtainable by the voltage relationship, I in value is known. So knowing the value of I in, you can say that I in plus delta IL by 2 will be the peak value here, I max value, and that will be the I max value. You have to rate both the BJT and the diode. The current rating for the devices. The average value of those will be the average current rating of the device, and for the diode peak inverse rating should be greater than V naught, and even for the BJT, the VCO rating should be greater than V naught, as we saw from the pole voltage waveform or the VP waveform. So that way you find the relationship of the input current and the output current in the case of the boost converter. Now if you look again at the boost inductor, boost converters inductor waveform, you will have the clue to find C. I will tell you how to go about. You can probably use it for practice, and then now this is the inductor current waveform, and this is IL, that is right, and the portion that supposed to flow through the diode is this. This is the portion that is supposed to flow through the diode. So I will say this is the diode current. Now this diode current splits into the capacitance and also into the load R naught. So what flows here will be IC, and what flows here is I naught, and this I naught is DC, and what flows here should be zero average. And we know that I naught, as it is specified, this will be the I naught value, let us say. This is what it should be. And what flows to the capacitor should be actually this ripple portion, and this is a huge ripple portion. So these two areas should match. This is for the capacitor. Now I naught value goes on to the R naught, and by Kirchhoff's current law here, the remaining portion is the diode current value minus I naught flows into IC. So minus I naught would mean for the capacitor this I naught line is the zero line. So which would mean this area as shown, this area should match this area for amp second balance. Now if I find the delta Q for this, I know that this height is I naught and this width is dTs. When the inductor current is rising, you know the area, that is the charge I naught into dTs, and this is equal to C delta V. So you have a way of calculating C, rearranging this. You have I naught D divided by delta V into Fs. So you see that I naught is specified, I naught is known, I naught is specified from the input, D is calculated from the input-output relationship, Fs is specified and given, delta V is a design spec. This should be a design spec. You will allow some amount of ripple on the capacitor. So based on that, the value of C will get calculated. So normally 10% of V naught is used for delta V and calculate the value of C. So this is how you will calculate the value of C. Likewise, you can calculate the value of inductor L2. So again, looking at the boost converter, we see that this is the inductor current waveform. The average value is In, and we know that In is equal to I naught by 1 minus D for the boost converter case. Knowing the value of I naught and D, we know the value of In. And what is this slope? This slope for inductor to charge on, the pole voltage is 0 during the time when the switch is on, and therefore this charge up current is Vin by L rate. So the charge up dIL by dt is Vin by, so when this goes down, this will be Vin minus V naught by L. As V naught is greater than Vin, this will be a negative slope, the falling slope. So you could use either of those slopes to evaluate the value of L. Vin by L, the rising slope here is having one variable, we could use that. So you will say Vin by L is nothing but dIL by dt, and as the wave shape rates are linear, they are straight lines, we will approximate it as delta IL by delta t. Now delta t in this case for this period is dTs, is the delta t. So we will say delta IL by dTs. Now these two parts we can combine together, and we have L, which is Vn into D divided by delta IL Fs. Ts has been put as 1 by Fs. This would be the value of the inductance, and you can calculate the L max using maximum value of D max. How to find D max? Use the relationship. You see, V naught is supposed to be kept constant. V naught is equal to Vn by 1 minus D. V naught is supposed to be regulated. So if Vn goes max, you would like to make the duty cycle min to get the same V naught value. Or if V in goes min, you would like to increase the duty cycle to get the value of V naught. So V in max and here it is V in min. V in max and V in min are known from the input spec tolerances, and using these two, V naught is known, it is also a spec, you can find out D min. Using these two equations, you could find out D max. So you can use D max here to find out the max value of L, if when you are doing the calculation for the value of L. Now that would give you the design equation for the inductance. Keep in mind now that we have only found the value of L, but we have not yet made the L, where you will need to have a magnetic core and you will have to calculate the number of windings and the air gap to be introduced to actually manufacture the inductor with the magnetics. The physical inductor needs to be manufactured to obtain a value as you see on the screen here. So how to go about manufacturing the inductance using the magnetics and the magnetic core, and how to wind it, all that I will discuss in the next week's lectures. Now consider the buck boost converter, the third of the primary converter. You recognize the topology, I suppose. Here you see that the inductor is in between, neither it is on the input side nor on the output side. You see that when the trans BJT Q is on, the inductor gets charged up by a current flowing from the input supply in this fashion, and when the BJT is off, the inductor current cannot be stopped, and therefore it will start flowing in this fashion, such that the inductor current is in the same direction within the inductor. And as a result, the capacitor will be charged with the polarity where the plus is here, and therefore you will get a negative voltage at the output. So this is the operation of the buck boost converter, which we studied before. Now let us see the waveforms at the critical point, that is at the pole voltage and also the inductor current. VG is the gate drive that you are giving to the BJT or any power semiconductor switch. When VG is high, the BJT is on. When VG is low, BJT is off. The definition of the time period is as shown here. DTS is the duty cycle T on time of the BJT, 1 minus DTS is the T off time of the BJT. So for this kind of gate drive, when you look at the VP or the pole voltage, when the BJT is on, Vin is appearing at the pole, and when the BJT is off, diode is conducting, minus V naught is appearing at the pole. So let us draw the waveform for that and position it here. So this would be the waveform that you would expect to see at VP, the pole. Now when the BJT is on, we expect to see this amplitude to be V in amplitude coming directly here, and when this is off, diode is conducting, negative of V naught will come in here because V naught is positive at this point. So you can expect to see a minus V naught at this point. The V naught, measuring at V naught itself, you will see V naught is negative, and it will have a negative value of DC as shown here. So this pole voltage gives the information for rating the voltage, for the voltage rating of the devices. When the BJT is on, this diode is off, the voltage across that is V in. V in at this point, and this is minus V naught. So the diode has to withstand the entire voltage which appears across this loop. So this whole height of this waveform from here to here is V in plus V naught. So you have a V naught and you have a V in. So this Kirchhoff's voltage loop equation, if you apply, that is the amount of voltage for the potential that the diode has to withstand. Or look at the pole voltage, the height from this point to this point the diode has to withstand, which is V in plus a V naught value. V in plus V naught is this peak inverse voltage, which should be greater than that. And when the diode is conducting, this device is off. When this device is off, this is at minus V naught and this is at V in. So V in minus of minus V naught, again V in plus V naught, the device has to handle. So you see that here the device ratings will be much higher than in the buck converter or in the boost converter. See, the buck converter has the least voltage rating, the boost converter the higher rating, and in the case of the buck boost converter you have V in plus V naught as the rating for the devices. And coming to the current wave shape for the inductor will be similar, except that the notation will change. This average value will be I in plus I naught. You see that the average value of the current which is flowing during the time when this is on, this is I in. During the time this is off, the current will be flowing here I naught. So average of I in and average of I naught both are combining and flowing through L. So the average value here will be I in plus I naught, and that is what we have indicated here. And likewise we have a positive slope, negative slope. When the BJT is on, V in by L is the positive slope, and when the BJT is off, minus V naught is appearing across L, and the downslope negative minus V naught by L. Now looking at the components, let us now look at the components of the inductor. First, let us look at the component that flows through the BJT. So this part of the inductor current, the blue part, flows through the BJT. The average value of this blue part is I in, and the peak value is, you know that the average value of the inductor current is I in plus I naught plus delta IL. So I in plus I naught plus delta IL will be the value. And for the diode current, the current that flows through the diode, you will see, let us position it like this. The yellow part is the current that flows through the diode, and average of the diode current is the I naught value. And like in the earlier case, probably I could show that the average of the diode current value is the I naught, just like in the case of the boost converter. And let me remove this waveform so that it becomes clear to see that this is the diode current wave shape as you would see on an oscilloscope. The rating for the diode you can take from this particular wave shape. So the inductor current peak value I in plus I naught plus delta IL by 2 will be the peak current value. Average value will be the I naught value. So these would be the ratings for the diode. In exactly the same manner, you can calculate the value of C as we did for the boost converter. You see, you take this wave shape, the area under this will be the delta Q, area under this will be the delta Q, I naught into 1 minus I naught into DTS would give you the during this time would give you the delta Q, and exactly like the boost converter value, you would get the value of C. And for the rating of the transistor here, we saw the blue waveform just now would also be like the diode current ratings. the peak rating will be I in plus I naught plus delta L by 2, and the average will be I in, not I naught but I in. So that will be the rating for this. I in you can find out knowing the D value and I naught. I naught is a spec given. So I in can be calculated. So I will leave it as an exercise for you to find out the value of L and the value of C along exactly the same manner that we did for the buck and the buck boost converter. If you are not able to get it, then bring it up in the forum and I will discuss that once again. So I will also put the simulation circuits for practice, so that you can practice the simulation and see the waveforms. Do the simulation of all the three converters and look at the pole voltage waveform and the inductor current waveform, not only for the buck converter which we did in the class, even for the boost and the buck boost converter.